Welcome to the instructional module for actuators beyond DC motors. In this module, we'll be covering several different types of actuators common to mechatronic systems. We will also go over some mechanisms that are commonly used for manipulating actuator force and speed.
DC motors are ubiquitous elements of electromechanical systems, which generate rotation and torque from electrical power. Brushed DC motors are the most common type and exert torques via the force exerted by a magnetic field on a rotating current. In brushed DC motors, brushes are used to control the direction of the current and result in force, a process called commutation. In brushless motors, the magnets on the inside of the motors rotate. Stepper motors are a class of brushless motor which utilize a toothed electromagnet designed to achieve incremental, rather than continuous, movement. These motors exhibit a holding torque when energized but stationary. DC motors are available in a wide variety of pre-packaged mechanisms which are useful for many applications. Servo motors are packaged combinations of DC motors, usually brushed DC motors, and PID control chips. They accomplish relatively simple position control and can be commanded using PWM methods very easily. Their ease of use and low price tag makes them very popular for many simple actuation applications. However, their accuracy isn't perfect, and the control loop is contained solely within the device, making them unsuitable for most high-precision applications. Linear actuators are mechanisms which combine a motor and gear assembly with a lead screw in order to provide translational motion and force. They are generally very slow due to the lead screw mechanism, but usually very reliable.
Hydraulic actuators are a favorite for high-torque industrial settings. These actuators can transmit very high forces that scale with its operating pressure. Since hydraulic actuators generally use an incompressible fluid, they are also capable of high force and position bandwidths. Hydraulic actuators can be rotary or linear. They can also be single or double acting. Single acting mechanisms transmit force or torque in one direction. They usually have return spring to reset its position and an inlet port for pressurized fluid. Double acting hydraulic actuators are capable of force or torque transmission in both directions. They generally have two inlets for pressurized fluid. The direction of actuation depends on which of the two inlets is used as the pressurized fluid flow. Despite its high forces and bandwidths, hydraulic actuators can have low efficiencies from pressure drops across the hydraulic valves. Wear from use or poor design of a hydraulic cylinder can also result in fluid leaks, which further decreases efficiencies and force outputs. Pneumatic actuators use compressed air instead of a pressurized fluid to produce actuation forces. They are also available as rotary, linear, single, and double-acting mechanisms. Like hydraulic actuators, they are capable of high forces, but since they use air, pneumatic actuators are inherently compliant. This adds an element of safety to them, but it also causes lower efficiencies and lower force bandwidths. Since air is compressible, pneumatic actuators display nonlinear behavior, which complicates their control. One interesting class of bio-inspired pneumatic actuators are called McKibben actuators. These actuators use compressed air to inflate an elastic tubing, which then contracts very similar to biological muscle. While these actuators are low weight and bio-inspired, they do require a more complicated controller from nonlinearities in its mechanical structure and pneumatic power. One major design choice behind using hydraulic or pneumatic actuators is their portability. These actuators generally need a pump or compressor, which can add to the overall weight of the system.
Piezoelectric materials are ones which change their shape in response to electrical current. These materials can be used to construct piezoelectric actuators. These actuators are robust and compact, capable of fitting into small profiles due to their relatively simple mechanisms. One type is the stack actuator, which uses a number of piezoelectric elements arranged in a stack to provide a single linear motion. They can be controlled such that they produce a single unified actuation, or as a number of discrete units allowing for a wide range of positions and forces. In either case, they usually provide high force and low displacement. Striped piezoelectric actuators, on the other hand, are single large piezoelectric elements. They provide a much lower force over a much larger range of motion, usually in a bending configuration. Shape memory alloys, as their name suggests, are materials that are able to remember a shape. After being set into a particular configuration and then deformed, the materials can be heated in order to restore them to their original shape. This process can be incited electrically via heat-inducing current. The most commonly seen of these materials is nitinol, an alloy of nickel and titanium. Most applications involving these materials use small quantities which exhibit large deflections and low forces. though the force-to-weight ratio of the materials tends to be very high.
Electroactive polymers use an applied electric field to produce actuation forces. These are often flexible materials and are lighter and have faster response times than shape memory alloys. There are two main classes of electroactive polymers, ionic and electronic. Ionic polymers are capable of bidirectional actuation, which is a function of the polarity of their applied voltage source. They work at lower voltages, but need an electrolyte solution to work properly. This complicates their design and possible integration into a mechatronic device. Ionic polymers also have lower bending forces and slower response times. Electronic polymers, on the other hand, have larger actuation forces and faster response times. They also have the added advantage of being able to hold their position with a constant voltage. These actuators don't need an electrolyte, but generally work at much higher operating voltages. While these actuators are likely not ready for widespread use, they are an interesting development with promising applications ranging from artificial organs to robotic space exploration. It is likely that they will be a promising actuator choice in the future. Oftentimes, transmissions are needed to change the output force or speed to a desired specification. Using a gearbox converts low force and high speed to high force and low speed. A gearbox has a reduction ratio that multiplies the motor torque and divides the motor speed. There are several different types of transmissions that may be useful in a mechatronic device. One is called a planetary gear train. These gears are named after their resemblance to planets orbiting a star. Different parts of the transmission can be used as the input or the output. For the highest reduction ratio, the central gear, known as the sun gear, is the input to the transmission, and the gears revolving around it, known as the planets, are the output. The right combination of gears can make these transmissions have a very high reduction ratio, and since load torques will be distributed across the planet gears, these transmissions are also high strength. Cycloidal transmissions are another high-strength and high-reduction mechanism that uses an eccentric disc and a set of rollers to provide a large gear reduction ratio in a very compact space. These transmissions also tend to have much less backlash or play, which makes them better than traditional gears for high-precision applications. Harmonic gears, also known as strain wave gears, are another interesting high-reduction transmission. These transmissions have zero backlash, which makes them particularly good for precision motion applications, but they are also much more expensive than the more traditional gears.
Other transmission options include belts and chains. Belts connect different rotating elements and unify their motion, transmitting loads between them. Depending on how they are configured, they can accomplish much the same functions as more complex gear arrangements, and are ideal for tasks where gears would be too large or cumbersome. However, they do tend to be constructed from weaker, flexible materials. Chains, which perform much the same tasks as belts, are made of rigid links which are more resilient to high heats and loads. They are, however, more limited in terms of flexibility and spatial constraints. For most projects, a combination of different transmission methods, dependent on specific mechanical needs, is ideal.
If you would like more information about any of these actuators covered in the instructional module, please check out these resources. Thanks for watching.